Welcome to the Joy of Architecture. Today we're diving deep into one of the most critical challenges in modern software design. Building systems that don't just work, but that stand strong and recover when things inevitably go wrong. We're talking resilience, especially in cloud-native and microservice architectures.
It really is fascinating, isn't it? Because the shift to distributed systems fundamentally changes the game. Back in the day, a single server failing, that was a major event.
Right. Big red alert.
But now, with maybe hundreds, even thousands of tiny services chatting over networks, well, individual components failing isn't some rare exception. It's just operational reality.
Yeah.
Networks hiccup, services get overloaded, dependencies vanish for a moment.
Exactly. So the question flips, doesn't it?
Oh, yeah.
It's less, how do we prevent any failure? And more, how does our system gracefully handle failures to minimize the blast radius?
Precisely.
And this deep dive is special because it's built just for you, our listener. It's based on a fantastic set of articles and research you sent us on this very topic.
Yeah, our mission today is really to cut through the jargon, pull out the essential patterns, those key knowledge nuggets from the sources you provided. We want to equip you with a solid understanding of how architects and developers actually build that resilience, that reliability into these complex systems.
Because it's all about keeping your applications up and running, performing well, even when things get rough.
Availability and performance under stress.
So what are the big ideas the sources kept circling back to? You mentioned this shift to microservices.
Yeah.
More failure points are just inherent now.
Right. Failure isn't something to avoid like the plague. It's something you have to actively design for.
The goal isn't perfection, which, let's be honest, is unrealistic. It's ensuring that when one piece fails, it doesn't bring the whole house down.
Exactly. Isolate the problem, maintain function, maybe even in a slightly degraded state, but keep the core working.
And the research you looked at has clear definitions for this.
It does. Resilience is framed as the system's power to withstand and recover from failures while still giving, acceptable service. Reliability is a bit different. It's more the probability that the system does what it's supposed to correctly over a period of time. Related, but distinct.
Makes sense. And the material we reviewed points to some core principles guiding this kind of design. Things like design for failure, automation, immutable infrastructure, limiting blast radius.
Robust observability, definitely. Loose coupling between services, asynchronous communication patterns, and having a culture of continuous improvement. Learning from failures.
And what's really interesting is how interconnected these all are.
Oh, absolutely. You can't really design for failure if you can't limit the blast radius, right? Or if you have zero observability to even know what failed. Automation, immutable infrastructure, those enable rapid recovery. Loose coupling, async messaging, they stop failures from spreading like wildfire.
And the sources connect these big ideas to concrete patterns the tools architects actually use. Like for designing for failure and limiting blast radius, we see retry, circuit breaker, bulkhead popping up.
Yeah, and automation relies heavily on things like infrastructure as code, CI/CD pipelines. Observability needs health checks, tracing, solid logging. Loose coupling comes from microservices themselves, event-driven approaches, API gateways. Async needs message queues or event streams, and continuous improvement. That's driven by post-incident reviews, maybe chaos engineering practices.
It's a whole ecosystem of techniques. So today, drawing from your sources, we're zeroing in on 4 really fundamental reliability patterns.
That's right. We're going to tackle retry, circuit breaker, bulkhead, and failover.
Okay, let's kick off with retry. This one feels pretty intuitive. Oops, try again.
Basically, yeah. The core idea is simple. Automatically reattempt an operation that just failed. But, and this is crucial, assuming the failure was temporary. You're betting that whatever caused it, a quick network blip, a service being overloaded for a second, a database lock will just clear up.
So the sources mention typical use cases like those transient network issues, a dependency being briefly offline, maybe database connection pool exhaustion, or hitting an API rate limit that resets quickly.
And a really critical point hammered home in the research is identifying transient errors correctly. Retrying something that failed because you sent bad data, a 400 bad request, or because you weren't authorized, a 401 unauthorized, that's pointless.
Right, it just wastes time and resources.
Exactly. It delays you finding the real permanent problem. Services have to be good at signaling which errors might be transient, like a 503 service unavailable versus permanent ones.
What about the pros and cons? Is retry always the right move?
Well, the sources often call it a double-edged sword. The benefits are clear: improved resilience, better availability by masking those tiny blips, and often a better user experience because the retry happens transparently. The user never even saw the hiccup.
Okay, and the other edge of that sword.
That's where the trade-offs bite. Every retry attempt adds latency. It uses more resources both on the client doing the retry and potentially on the server being hit again. But the big danger, the one really emphasized, is the risk of retry storms, the thundering herd.
Ah, yes, the classic anti-pattern.
Definitely. If loads of clients all start hammering a struggling service with retries at the same time, boom, you can completely crush it, preventing recovery. Plus, implementing sophisticated retry logic adds complexity. And relying too heavily on retries without good monitoring can actually mask underlying issues that need a proper fix.
Okay, so where would our listeners typically see this pattern implemented? Is it everywhere?
It's pretty common, built into various layers. Cloud provider SDKs are a big one. Azure SDKs often have retry policies baked in. Azure Service Bus handles message reprocessing. Azure API Management lets you configure retries. On AWS, their SDKs usually have automated retries with exponential backoff and jitter. Step Functions lets you define retry logic. SQS uses dead letter queues for failed messages after retries.
Yeah, and Google Cloud. Similar story.
Yeah, Google Cloud Client libraries often include retry logic, usually with truncated exponential backoff plus jitter. Even command line tools like gcloud might auto-retry some things, and GCP docs specifically recommend backoff with jitter for certain API calls.
What about beyond the big three open source libraries?
Absolutely. Libraries are hugely popular for application-level control. Poly is a well-known, comprehensive choice for .NET. Resilience 4J is kind of the standard in the Java world, very configurable. Spring Retry offers neat declarative annotations in Java. And then you have service meshes like Istio. They can handle retries down at the network infrastructure level using the Envoy sidecar proxy.
Offloading it to the infrastructure level. That sounds appealing. Less code for the app developer to write.
It can be. It allows for centralized policy management, which is nice. The sources definitely highlight that difference in approach SDK convenience versus library control versus mesh transparency.
Can you paint a picture of the flow? How does the retry mechanism actually work architecturally?
Sure. Imagine your client isn't talking directly to the target service. There's a sort of retry handler sitting in between. The sequence goes: client sends request to handler, handler forwards to target, target returns a transient error, say of 503. The handler catches this, it checks, is this error type configured as retriable? Have we hit the max attempt limit? If yes to both, it calculates a delay. And this is key. It uses a backoff strategy, often exponential, plus some random jitter.
Jitter. That's to stop everyone retrying at the exact same millisecond, right?
Precisely. Prevents that thundering herd. So it waits for that calculated delay, then sends the request again. This repeats until either it gets a success, which it passes back to the client, or it hits a limit. Max attempts, non-transient error. Then it gives up and passes the final error back, or maybe triggers a fallback. That decision logic in the handler is the heart of it.
So when you're running systems with retries in production, what do you really need to keep an eye on, operationally speaking?
Observability becomes absolutely critical. You have to log every retry attempt. Why it happened, the delay used, the outcome of that attempt, and the final outcome of the whole operation. Without that logging, debugging transient issues is a nightmare.
And metrics.
Definitely. Track the retry count and rate per dependency. Track the success rate after retries. Are they actually helping? Track the failure rate after hitting max attempts. Monitor the added latency from retries. Are they making things too slow? And track if retries are being throttled. These metrics tell you if your strategy is working or just adding noise and load.
So alerts would trigger on sustained high retry rates.
Yeah, or frequent failures, even after all retries. Those usually indicate something more serious is going on, not just a transient blip. The sources are clear. You need this operational feedback to tune things properly.
Tuning. That sounds like where the real art comes in. What parameters are most important?
Oh, it's crucial. Default settings rarely work perfectly everywhere. Key parameters the sources highlight: maximum attempts, often 3 to 5 is a starting point, but it really depends. The delay or backoff strategy, like we said, exponential backoff with jitter, is the gold standard. It prevents collisions and spreads load. You'll also tune the initial backoff delay, maybe a maximum backoff limit. A timeout per retry attempt is important, so one attempt doesn't hang forever. And an overall timeout for the entire operation, including all retries. You need a point where you just give up. And maybe the most critical, defining exactly which exceptions or error codes are actually retryable. Don't retry things like 400s.
Right. Only the ones that might actually resolve themselves.
Correct. And tuning is iterative. You look at your monitoring data, how long do failures typically last, how many retries does it usually take, and adjust accordingly.
What if, after all the retries, it still fails? What's the plan B?
You need a defined failure handling strategy. Options include propagate the final error up the chain, return some kind of fallback response, maybe cache data, a default value, a simplified result. Always log the final failure details. For really critical things, you might need to escalate it, trigger an alert, or even initiate compensating transactions if it was part of a larger workflow.
Given the pitfalls like retry storms, what are the absolute must-do best practices and common mistakes the sources warn against?
Top best practice, mentioned everywhere. Ensure idempotency. Any operation you retry must be safe to execute multiple times without unintended side effects. Think charging a credit card retrying that needs extreme care?
Definitely don't want to double charge someone.
Exactly. Other best practices. Always use exponential backoff with jitter. Limit retry attempts, never infinite. Configure sensible timeouts per retry and overall. Explicitly distinguish transient from permanent faults. Log and monitor everything related to retries. Consider the context user-facing versus background job might have different needs. And please, leverage existing libraries or platform features. Don't reinvent this wheel, it's tricky to get right.
And the pitfalls, the anti-patterns.
The big one is the retry storm thundering herd caused by simultaneous aggressive retries without backoff. Also, retrying non-transient errors wastes resources, hides the real problem. Infinite or excessive retries lock up resources. Ignoring idempotency leads to data corruption or worse. Not using backoff jitter makes retries ineffective and contributes to load. Hiding failures too much with retries can mask serious underlying issues. And using one global retry configuration for everything rarely works well. Different dependencies need different tuning.
I can see how a simple mistake, like just looping on any exception without limits or delay, could quickly lead to disaster.
Oh, easily. That's probably the most common naive implementation, and it causes so many problems. These best practices aren't suggestions, they're pretty much essential.
Any specific case studies or industry examples that really illustrate the impact?
The sources mention a few. DoorDash shares concrete recommendations. Exponential backoff plus jitter, maybe 3 attempts, 1 to 5 second initial delay, use libraries. Uber talked about using client-side retries for their data store, safer with idempotency, and challenges adapting retries for Kafka. There's an anecdote about a payment API using Spring Retry, seeing a 60% drop in timeouts and 90% fewer circuit breaker trips. That's tangible.
Wow, yeah.
Research like Resilience Bench confirms retry is effective at low to moderate failure rates, but stresses combining it with other patterns like circuit breakers when failures are more frequent, as retries alone can worsen things under high load. There's even ongoing research into dynamic adaptive retries. The takeaway is retries work, but configuration is king, and context matters immensely.
Okay, fascinating stuff. Let's switch gears to the next pattern, often a partner to retry, but with a very different job. The circuit breaker, where retry says try again, circuit breaker says hold up, stop.
Exactly right. Think of that electrical circuit breaker in your house. Too much current. It trips open to stop the flow, preventing damage. The software circuit breaker pattern is a stateful mechanism. It watches calls to a dependency. If it sees too many failures or timeouts, it trips open. Once open, it immediately rejects further calls without even trying to contact the downstream service. This protects the caller and gives the struggling dependency a break.
And the sources mentioned it has 3 distinct states.
Yes, closed, open, and half open. Closed is the normal state. Requests go through, but the breaker is watching failures, maybe slow calls. If a threshold is breached, snap, it trips to open. In the open state, all requests are immediately rejected. Fail fast. It stays open for a set, reset timeout period. Think of it as a penalty box duration. After that timeout, it doesn't go straight back to closed, it goes to half open.
Half open, like cautiously peeking out.
Pretty much. In half open, it allows just a small, limited number of probe requests through to the dependency. It watches these probes very carefully. If enough probes succeed, great. The breaker assumes the dependency has recovered and transitions back to closed. If the probes fail, nope, back to open, restart the timer.
Use cases seem clear. Protecting your app from slow or failing dependencies, stopping failures from cascading, managing calls to unreliable third parties, making the system feel more responsive by failing fast instead of hanging.
And crucially, giving that struggling service breathing room by stopping the barrage of requests. That reduction in load is key for recovery.
So, comparing it directly to retry.
Retry is optimistic about transient issues, keeps trying, with delays. Circuit breaker is pessimistic based on recent history. It actively stops calls when failure seems persistent. It's stateful, remembering past failures.
What are the big wins with circuit breakers, and what are the complexities or trade-offs?
The number one benefit, stressed everywhere, is preventing cascading failures. It contains the problem. This leads to much improved resilience and stability overall. You get that fail-fast behavior, huge for user experience compared to long hangs. It protects the client's resources, threads, connections. The half-open state gives you automatic recovery detection. And, as we said, it reduces load on the failing service, aiding its recovery.
Sounds powerful. The trade-offs, I'm guessing managing those states and thresholds isn't trivial.
Definitely not. The main trade-offs are increased complexity.
Yeah.
You're managing state, counters, timers, thresholds. It's significantly more complex than a simple retry loop. It has high configuration sensitivity. Getting those thresholds right, failure rate, slow call rate, minimum volume, reset timeout, number of half-open calls is critical and dependency specific. Misconfigure it, and it trips constantly or way too late.
False positives or letting the fire spread.
Exactly. There's potential for false positives, especially with low traffic volumes or noisy metrics. And if the circuit stays open for a long time because your fallback isn't great, users experience fallback fatigue, and you might mask an underlying issue that needs fixing.
So a vital shield, but needs careful tuning informed by observability, specific to what it's protecting. How do people actually implement this?
Again, various layers. Cloud platforms have related services. Azure API management can apply policies based on backend error rates. Azure Load Balancers gateways use health probes to route away from unhealthy instances, similar concept at the LB level. On AWS, you might build logic using step functions or use libraries within EC2 Lambda. CloudWatch alarms could trigger state changes.
And GCP?
Often relies on client libraries or a service mesh. You can use Resiliency 4J or similar within apps on GKE Cloud Run functions. Istio on GKE offers powerful circuit breaking via Envoy's outlier detection in destination rules.
You mentioned libraries again, which are the go-to ones.
Poly for .NET has solid circuit breaker policy. Resilience 4J is the dominant Java choice. Very flexible with count time windows, thresholds, wait durations. Netflix Hystrix was the pioneer here. Hugely influential, though now in maintenance. Bundled breakers with bulkheads and fallbacks. Failsafe is another Java option. These libraries give you fine-grained control right in your application code.
Can we walk through the state machine flow visually? How do requests navigate those states?
Okay, start and closed. Request comes in, goes through the breaker to the downstream service. Breaker monitors the outcome success, failure.timeout. It updates its stats, e.g. failure count in the last minute. If the failure rate or slow call rate crosses the configured threshold, failure rate threshold, over a certain volume, minimum number of calls, bang, transition to open, start the wait duration open state timer.
And once it's open?
Any new request hits the breaker and is immediately rejected. Fail fast, no call to the downstream service. It just sits there rejecting calls until that timer expires. Timer up, transition to half open.
The cautious state.
Right. Now, it allows just a few requests through the number defined by permitted number of calls in half open state. These are the probes. It watches their results. If enough probes succeed, meeting some internal success threshold, it assumes recovery and transitions back to closed, resetting everything. Happy path. But if those probes fail, it snaps right back to open, restarts the timer. No recovery yet. That state logic is the engine of the pattern.
That statefulness definitely adds operational wrinkles. What needs close monitoring and careful tuning?
Oh yeah. For monitoring, you absolutely need metrics on the current state of each breaker. Closed, open, half open. Track call volume permitted versus rejected. Monitor the failure rate and slow call rate the breaker is seeing. Crucially, track the success rate during half open that tells you if recovery attempts are working. Measure latency of permitted calls. Track the number of state transitions flapping, indicates instability or maybe bad tuning. And if you use fallbacks, monitor fallback metrics.
And what should trigger alerts?
Definitely alert if a breaker gets stuck open or half open for too long, persistent dependency issue. Alert if circuits are tripping too often, maybe thresholds are too sensitive, or the dependency is very flaky. High fallback rates or sudden shifts in the underlying failure latency metrics are also key alerts. The sources really emphasize using this data to iteratively tune the parameters.
Tuning sounds even more critical here than with retry.
It is, because the states introduce more variables. Defaults are almost never right. You tune failure slow call thresholds based on the dependency's specific behavior and your SLOs. The sliding window type, count versus time, and sliding window size affect reactivity. Minimum number of calls avoids tripping on tiny traffic bursts. Wait duration open state, reset timeout is a huge one. Too short, no recovery. Too long, unnecessary outage extension. Permitted number of calls in half open state needs to be just right. and you configure which exceptions count as failures. It's a constant balancing act informed by production data.
What's the typical failure handling when the circuit is open and rejecting calls?
The most common and recommended approach is fallback. Instead of just erroring out, you provide an alternative. Cache data, a default response, maybe a degraded version of the feature. The quality and usefulness of the fallback are really important for user experience. If no good fallback exists, you propagate an error, often an HTTP 503 service unavailable, signaling the dependency is down.
Okay, let's talk best practices and pitfalls for circuit breakers. What are the key takeaways?
Best practices. Configure sensible, robust fallbacks. They define the degraded experience. Use granular circuit breakers, one per dependency operation usually makes sense. Tune thresholds carefully and iteratively using real data. Monitor state and metrics actively. Test behavior. Rigorously use chaos engineering, fault injection. Combine strategically with retries, maybe a quick retry before the breaker logic kicks in for very short blips. Educate your teams on how they work and how to interpret their behavior.
And the common mistakes.
Pitfalls include overly aggressive thresholds causing false positives, overly lenient thresholds letting failures spread too long, inappropriate open durations too short or too long, fallback fatigue or just plain poor fallbacks that frustrate users or hide problems, ignoring half-open results so the circuit never recovers properly, using global breakers without synchronization, per instance, is common. Critically, not testing fallback logic, it has to work when things are already broken, and misusing it for business logic validation instead of dependency protection.
The sources mentioned a really important operational lesson, especially from Netflix's Hystrix experience.
Oh yes, the instant when a circuit trips or shows high latency is often, quick, increase the thread pool, raise the limits, but Hystrix found the breaker is usually doing its job by shedding load. The problem is almost always the downstream dependency. The focus should be fixing that, not trying to force more traffic through a broken pipe.
That's a great insight. Any major case studies?
Netflix Hystrix is the classic. They didn't just build the library, they shared tons of operational knowledge, like tuning timeouts near the 99.5th percentile. Error Spike database uses client-side breakers to stop clients overwhelming the cluster during partial failures, protecting the backend. Microsoft Azure documents it heavily and provides it in APM. It's a foundational pattern in finance, e-commerce, streaming, anywhere. High availability and low latency are critical. Hystrix really set the standard for operationalizing these patterns.
Right, 2 down, 2 to go. Let's move to the Bulkhead Pattern. This feels less about reaction, retrip, and more about proactive containment, like partitioning resources.
That's a perfect way to put it. Bulkhead is all about isolating elements into distinct pools or compartments. The idea is if one compartment fails or gets overloaded, it's contained. Others keep running. The analogy is those watertight bulkheads in a ship's hull. Breach one section, the water is contained, the ship stays afloat. Software bulkheads partition resources, threads, connections, CPU, memory, even service instances to limit the blast radius of problems.
So use cases could be isolating calls to different downstream services. Slow, service A doesn't starve resources needed for fast service B.
Exactly. Or separating critical functions from non-critical ones, giving critical paths dedicated resources. Partitioning resources within a service, like read versus write thread pools. Tenant isolation in multi-tenant systems is a big one, protecting against the noisy neighbor effect. Generally, preventing resource exhaustion is the core goal. One failing part shouldn't drag down the whole system by hogging all resources. And at a larger scale, cell-based architectures are essentially an advanced bulkhead strategy.
Cell-based,
Yeah.
meaning you partition the whole system.
Yeah, into independent cells, each handling maybe a subset of users or requests, often with their own isolated data stores. A failure in one cell doesn't impact others. Amazon uses this heavily.
So the core idea is containment through resource partitioning. Failure in one bulkhead only uses up its resources.
Correct. It hits the limit for that compartment only, triggering rejections or queuing just for that workload, while others continue unaffected. It avoids the single shared pool of death scenario.
What are the main benefits and the associated costs or trade-offs?
The huge benefits are fault isolation and preventing cascading failures. Containing the impact is key. This leads to preserving partial functionality. Unaffected parts keep working, resulting in improved resilience and availability. You can also offer tailored quality of service by giving critical paths bigger or faster pools. And as mentioned, protection against noisy neighbors.
The trade-off seems like it might be resource efficiency, having lots of small pools versus one big one.
That's the main one. Increased resource overhead. Multiple small pools often need more total resources than one large shared pool, and some might sit idle. This leads to configuration complexity, defining the bolt heads, sizing the pools correctly, routing requests. There's potential for resource fragmentation if sizing is off, and more management overhead, more pools or components to monitor. The trade-off is isolation versus cost and complexity. Granularity is the balancing act.
Where do people implement bulkheads? Is it infrastructure, application code, or both?
All of the above. At the infrastructure level, in Kubernetes, AKS, SGK, you use pod resource limits, namespaces, node pools. Cloud providers offer separate compute instances or plans, like app service plans. AWS promotes cell-based architectures. Serverless platforms like Lambda or Cloud Functions provide invocation, isolation, and concurrency limits.
And within the application itself?
Libraries are common here for finer control. Resilience 4J in Java has a bulkhead module with semaphore or thread pool options offering different isolation guarantees. Poly for .NET has a bulkhead policy. Netflix Hystrix pioneered thread pool isolation per dependency. And service meshes like Istio can act as a network-level bulkhead by limiting connections per service via destination rules.
So you can layer these approaches. How does it look architecturally?
The common diagram shows a client app talking to a dispatcher. Instead of one pool, the dispatcher routes requests for service A to pool A, service B to pool B, etc. If service A gets slow and pool A fills up, requests only for service A get rejected from pool A. Requests for service B go to pool B independently. The other view is the cell-based architecture, showing completely separate vertical slices, compute, data, everything, with a smart routing layer directing traffic to the right cell.
Can you walk through the sequence flow for, say, a thread pool bulkhead?
Sure. A request comes in needing data from service X and service Y. To call service X, it needs a thread from thread pool X. If available, Great makes the call, releases the thread. If thread pool X is full, maybe service X is slow, the request for X is rejected immediately, or queued if configured by that bulkhead. Crucially, this rejection for X has zero impact on getting a thread for service Y. It tries to get a thread from thread poolie. If that pool has capacity, the call to Y proceeds. Service X's problem is contained.
Makes sense. Operationally, what are the big things to manage with bulkheads?
Granularity is key. How many pools? What does each protect? Too coarse, little isolation, too fine. Complexity and fragmentation. You align it with failure domains and criticality. Resource allocation sizing the pools. Threads, connections, permits. This needs load estimates, performance knowledge. Static sizing is hard, too small. Premature rejection, too large. Wasted resources, less containment.
Monitoring must be vital for getting that sizing right.
Absolutely essential. You need metrics per bulkhead. Pool utilization, active versus size. Rejection rates, requests rejected due to fullness. Wait times, if queuing. Plus overall system monitoring. Alert on consistently full bulkheads, high rejection rates, long queues. This feedback loop is how you tune the sizing and granularity.
And when a bulkhead does reject a request because it's full?
Failure handling is similar to circuit breaker. Fail fast is common return an immediate error. Or invoke a fallback for that specific dependencies call. Some implementations allow queuing, buffering spikes, but adding latency and complexity.
What are the best practices and common pitfalls for bulkheads?
Best practices. Isolate by load, availability needs, criticality. Combine with other patterns, retry CB. Determine appropriate granularity. Monitor performance per bulkhead. Choose the right isolation technology. Threads versus processes versus containers versus nodes. Allocate resources appropriately. Implement robust monitoring. Define clear failure handling. Common pitfalls. Overly granular or coarse bulkheads. Incorrectly sized bulkheads, the big one. Shared resources between bulkheads, a single shared database pool, disk I/O bottleneck, etc., undermines the isolation completely. Not monitoring bulkheads means you're flying blind, adding complexity without real benefit. The monolith in microservices anti-pattern, where tight coupling negates resource isolation. And assuming isolation is absolute, it isolates resources, not logic bugs or data issues.
That shared resource point seems critical. You really have to think about all potential contention points.
Yes. CPU, memory, network, disk I/O, database connections, external service quotas. True isolation requires holistic view.
Okay, last pattern for today. Failover. This is the plan B for when something actually breaks, right? Switching to the backup.
Exactly. Failover is a reactive strategy focused on availability and continuity. It automatically redirects traffic or shifts work from a failed component to a redundant standby. Minimize downtime is the name of the game.
Use cases seem obvious. High availability for critical services, disaster recovery to another site or region, database failover to a replica, Load balancers skipping unhealthy instances.
Right, handling stateless service failures by just using another instance. Stateful service failover is more complex, needing state replication.
And the sources mention two main models, active-passive and active-active.
Correct. Active, passive, or standby. One primary handles traffic, a passive standby is ready. Primary fails. Promote passive, redirect traffic. Think pilot light or warm standby, dir active-active. Multiple components or sites actively handle traffic simultaneously. One fails, others absorb the load. Often spans availability zones or regions. Lower recovery time, but more complex, especially data consistency.
So failover uses redundancy to recover from failure, and the model choice depends heavily on business needs RTO and RPO.
Precisely. RTO recovery time objective max allowed downtime. RPO recovery point objective max allowed data loss. Failover strategies are designed to meet these. Near zero RTORPO usually means complex, costly active with synchronous replication. Higher RTORPO allows simpler, cheaper options like backup restore or active-passive with async replication.
What are the core benefits and the inevitable trade-offs?
Benefits are clear. Minimized downtime, high availability, improved reliability, business continuity. With replication, it aids data protection, meeting RPO. Automated failover means faster recovery, meeting RTO.
Trade-offs mostly around cost and complexity.
Yes. Cost of redundant infrastructure.
Yeah.
Complexity in design, implementation, testing, management, especially stateful systems, data sync, conflict resolution. Switch over time isn't zero, it impacts RTO. Potential data loss depending on replication. Async versus sync impacts RPO. Risk of split brain if not handled carefully. And failback complexity, going back to the original primary safely, is often tricky. It's a balance based on requirements, risk, budget.
Where do we see failover implemented? Cloud platforms seem big here.
Oh yeah, cloud providers offer extensive managed services. Azure Site Recovery for Docker Azure Load Balancer App Gateway, for instance, failover via health probes. Azure Traffic Manager for DNS-based global failover. Azure SQL DB, Cosmos DB have built-in HA and geo-replication with auto failover options. AKS Service Fabric provide instant self-healing. Similar story, Route 53 for DNS failover, EOB for instance failover, AWS Elastic Disaster Recovery, DRS, RDS Multi-AZ Aurora Global DB, DynamoDB Global Tables for database, HADR. Auto-scaling groups replace failed instances. Their well-architected framework details various DR strategies.
And GCP.
Cloud load balancing with health checks and failover configs. Cloud DNS, managed instance groups, MIGs with auto-healing. Cloud SQL Spanner Firestore HA options. And foundational tech. Kubernetes provides basic pod self-healing. Service meshes like Istio add sophisticated outlier detection and locality-aware failover. Service discovery tools, Consul, Eureka, help clients find healthy instances. Traditional tools like Keep Alive Data Proxy handle VIP failover and load balancing.
So lots of options. Operationally, what's critical?
Monitoring health of all components, primary and standby. Monitoring replication lag. Monitoring the detection mechanism. Monitoring the failover process itself, how long did it take. Tuning involves health check parameters, detection thresholds, routing policies, replication settings, sync-async. Automating the failover is crucial for RTO.
What happens during the failover itself?
Ideally, traffic is seamlessly redirected. In-flight requests to the failing primary might fail. Clients might need retry logic aimed at the new endpoint. Managing connections and state during transition is complex.
Best practices and common pitfalls for failover.
Best practices. Design for automated failover. Implement comprehensive health monitoring. Test failover and failback. Rigorously, this is the big one. Ensure data consistency meets RPO. Use granular failover where possible. Plan failback carefully. Common pitfalls. Neglecting testing. Assuming automation is flawless. Underestimating data sync challenges. Not handling split brain correctly. Lack of observability into the process. Over-reliance on manual steps. Underestimating stateful failover complexity. Failing to plan test failback.
Testing. That seems to be the recurring theme, especially here.
Absolutely critical. If you don't practice failover and failback regularly, it simply won't work when disaster strikes.
Any specific case studies?
While companies rarely publish detailed postmortems of failover events, Amazon's well-architected DR strategies serve as industry guidance. Major cloud outages often become unintended case studies, highlighting the need for multi-zone or region strategies. Companies known for resilience, like Netflix, constantly refine these approaches. It's a fundamental practice across industries needing high uptime.
Wow. Okay, we've covered a lot of ground today. Retry for transient errors.
Yeah.
Circuit breaker to stop hitting broken dependencies. Bulkhead to contain failures via resource isolation. And failover to switch to backups when things truly fail.
And these aren't just abstract ideas, right? They're practical, battle-tested patterns that are absolutely essential for building systems that can actually withstand the chaos of modern distributed environments. They let systems handle failure gracefully.
Understanding these patterns, their nuances, how to operate them, that really equips you, the listener, to design and build more resilient applications. Applications that stay available and keep users happy, even when components fail.
Yeah, and maybe a final thought to leave folks with, drawing it all together from the sources. True reliability rarely comes from just one of these patterns alone. It's usually about combining them strategically. You might use retries first, then have a circuit breaker trip if retries fail consistently. Bulkheads protect the resources those patterns use. Failover is the ultimate safety net. Resilience isn't a one-time fix. It's this ongoing journey of engineering, testing, monitoring, and learning from every single failure to make the system incrementally stronger.
That's a really powerful point. It's a continuous process. Well, thank you for providing the sources that fueled this deep dive. Stay tuned for future episodes by subscribing to Joy of Architecture.